Ladies and gentlemen, welcome on the first talk of our afternoon session. Our speaker is Johanna Knapp from University of Melbourne. She's an expert in string theory, and she's going to talk on the exploring distance corner of Calabi-Yau moduli spaces. Please join me in greeting our speaker.
All right, so at first I would like to start thanking the organizers for inviting me to this impressive, massive event. I had a great 2 weeks and it's a pleasure to speak here. So this talk is going to be about regions in moduli spaces of Calabi-Yaus, which are perhaps not as well studied as other regions. So here's the outline of my talk. So I'm going to spend a lot of time actually to give a bit of context. This is supposed to be an overview talk. It's like after lunch and late in the conference. And clarify what kind of questions I want to ask and what kind of problems I would like to address in this context. And then I will also introduce the main tool that I want to study this, which comes from physics, which is the gauge linear sigma model. And I also want to thank the previous speakers of today to already set the stage a little bit. And then, depending on how much time I will have left, I will do a lot of examples. So I start off with the quintic. I think this place is probably the best place in the world to talk about the quintic, so I will take this opportunity. And then I'll gradually move on to more complicated examples. So one class of models I want to discuss are so-called hybrid models. I will explain what that is and give examples. And then I want to come back to geometry, basically, that appears in some corners of the moduli space, but in a sort of unusual way, and I would like to call this non-perturbative geometry. All right, so this is, as I said, going to be an overview talk. So I've been working on this basically my whole life, so I want to acknowledge my collaborators, lots of whom are actually here, so it's a very challenging audience because of this. And I'm not going to talk about a specific paper, so I just listed a few more recent ones. The papers we are writing are usually very long and very technical, but very recently my postdoc Joseph McGovern and I wrote a short proceedings article that exhibits many of the phenomena, is a toy example that exhibits many of the phenomena I want to talk about. So if you want something entertaining to read on your trip back home about a Calabi-Yau that is zero-dimensional, I recommend this one. All right, so let's get started. So also in the morning, Mauricio talked about the blast from the past and physics of the 90s. So I'm going to discuss a very, very classic topic in string theory. So what we're going to consider is something fairly vanilla in principle, so type 2A or type 2B string theory compactified on some Calabi-Yau threefolds. Sometimes I will add D-branes to the setting. As we all know in string theory, the problems become much more interesting if you're not just considering a Calabi-Yau alone, but in combination with its moduli spaces. And that also, of course, applies in the context when we study perturbative and non-perturbative quantum corrections in string compactifications, the moduli play an important role. When we think about a Calabi-Yau compactification, we typically have this very standard cartoon in mind. So we have some 4D spacetime and then some internal smooth geometry with some extra structure that may come from D-branes or fluxes. And very often we think about examples like the quintic. So depending on where we are in the moduli space, this like simple geometric picture of a compactification in a smooth Calabi-Yau manifold may not necessarily be accurate. And this is basically what this talk is going to be about. So let's zoom in on the moduli spaces. So what I've drawn here is a cartoon of a stringy moduli space for one parameter Calabi-Yaus. So we're assuming that either the Kähler moduli space or the complex structure moduli space of the mirror in this picture is complex one-dimensional. And the regions of the moduli space, which are captured by the picture on the previous slide, is usually called the large volume limit in the Kähler moduli space or a large complex structure limit. And you can associate various properties on these like well-studied limiting points in the moduli space. So for instance, these geometric regions have maximally unipotent monodromy, for instance. So what I'm interested in now is to move away from these well-studied points And if we do that, we're going to move inwards in the moduli space, not only infinitesimally, but like at a finite distance. And we typically will encounter some singularities. So in the Kähler moduli space, you would at some point hit the boundary of the Kähler cone. And then you can move on, so to say, to the other end of the moduli space. And these are the regions that I want to study today. So there is in the complex structure side, this is a global picture. We're thinking about periods and differential equations. So the going from here to there more or less corresponds to change of coordinates, versus in the Kähler moduli space picture, it's really a notion of analytic continuation. So you're moving beyond the boundaries of a Kähler cone of a Calabi-Yau, and you're seeing the whole stringy moduli space. So I'll now have, yes? No, passing through. Oh, facets, basically. Yeah. So I will make them more precise as I go along. But please keep asking. All right. So the main question of this talk is to be, what is this something else in other limiting regions of the moduli space, which are not like large volume? And before I come to that, I want to ask a few related questions, namely how many ways there are that we can study or characterize string theory on the Calabi-Yau threefold. So of course we can have the standard picture. We take the full type 2A, type 2B string theory and compactify on a Calabi-Yau. But there are also other ways to approach a Calabi-Yau compactification. So for instance, as we have heard, for instance, in your talk, there is a lot of Calabi-Yaus can be understood in terms of toric geometry. So for instance, this well-understood region in the moduli space will be a maximal star triangulation of a reflexive lattice polytope in the Kreuzes-Gager list, and you can do a lot of analysis in this context. You can also characterize these well-understood regions in the properties of the moduli spaces and the monodromy, for instance. So there, a point of maximally unipotent monodromy is what happens, what is a large volume or large complex structure point. Especially in the context of topological string theory, we can really just zoom in on the Calabi-Yau and think about nonlinear sigma models, which are target spaces of Calabi-Yau, with Calabi-Yau target spaces. What I will spend a lot of time on in this talk is to understand this as a phase, so a low energy effective theory of a gauged linear sigma model where the vacuum manifold is a Calabi-Yau. So the solution to the vacuum equation is on the Higgs branch. And then if you want to take the full worldsheet perspective and not care too much about geometry, you can also characterize a Calabi-Yau as a 2,2 superconformal field theory with central charges 9,9. So what I want to tell you in this talk is that in principle, all of this can be true, but it doesn't have to be true to have a notion of a Calabi-Yau compactification. All right, so let's move on and ask more questions. So I will always assume in the talk that I will have at some point in the moduli space a region that I understand very well, that is sort of satisfies all these bullet points of a Calabi-Yau compactification. So the question we then want to ask is, if I want to go to another asymptotic region in the moduli space, what can we expect to find? So for instance, is there another geometry or another nonlinear sigma model? And sometimes the answer is going to be yes, and I will have examples like of that. Sometimes it's no, and then the question is, what is the correct mathematical and also physical description to describe these other regions in the moduli space? And this is usually a hard question, but sometimes we can answer it, and also there I will have some examples. Another question we can ask, since we like toric complete intersections, is if something interesting happens when the Calabi-Yau is not a complete intersection in toric spaces. And I will also hopefully come to a few examples to convince you that the answer to this is yes, and that it pays off to look at non-toric Calabi-Yaus. And of course, if we are, as physicists, the main question we want to ask is, can we actually calculate something? And I think the answer is very much yes, but often the question is how to interpret what you're actually computing. All right, and another question that naturally arises if you look at the global structure of the moduli space of a Calabi-Yau is if there is some universal language that holds everywhere in the moduli space, that doesn't necessarily rely on having a smooth, compact geometry. And the reason why this should exist, basically, comes from the fact that we always have a worldsheet CFT somewhere in the IR. So the CFT language seems some sort of universal, and also the gauge linear sigma model, as I will introduce it, also sees the global structure in the moduli space and doesn't really rely on the geometry. All right, even more questions? Yes.
Picture?
Yes, so I would like to have, I will be a bit more precise later on, but I would like to have objects that I can define everywhere, at least in the asymptotic regions in the moduli space, that doesn't rely on the concrete realization of the CFT.
Thank you.
Okay, that actually very much brings me to the next question slide, is the last one. What are the objects we can study, and why do we expect to have a universal structure somewhere? So this doesn't necessarily apply to all objects, but there are topologically protected objects that we expect to sort of persist throughout the moduli space. So we shouldn't lose any information about certain objects when we move through the moduli space, but we should need probably a duality or a formulation to match objects at different loci in the moduli space. So knowing very well how we can do calculations on smooth Calabi-Yau threefolds, we can ask what are the equivalent concepts when we go to the other ends of the moduli space. So for instance, if a physics description in terms of a nonlinear sigma model no longer applies, what do we replace it with? Or as I said, in Calabi-Yau compactification, we also have a some CFT in the IR. So this in a standard Calabi-Yau compactification, the state spaces of the CFT, the quantum state spaces, like the chiral rings that we can compute, they are related to cohomology classes on the Calabi-Yau. So we also should find a replacement of that. So if we have these state spaces, we can also insert them into correlation functions. So, and especially in the topological sector, when we take certain chiral ring element and insert it into in the correlator. If we do that in a Calabi-Yau nonlinear sigma model setting, this would be called a Gromov-Witten invariant. But if we are somewhere in the moduli space where these descriptions are not accurate, we can ask ourselves what are the equivalents of Gromov-Witten invariants in this limiting, in these other limiting regions of the moduli space. And then finally, I also want to mention D-branes a little bit, and the category of D-branes that is well under control in this context is the B-type D-branes. And in a Calabi-Yau setting, these would be objects in the bounded derived category of coherent sheaves. So when we are not necessarily in a geometric region of the moduli space, we also have to ask ourselves how to characterize B-branes when we cannot think about branes wrapping holomorphic cycles. So these are the questions that I want to address for these distant regions in the moduli space, and I'll see how far I get with answering those. So since I see quite a few experts in the audience, I also need to sort of manage expectations a little bit. So here's my disclaimer slide. So what I will mostly restrict to for simplicity in my talk is one parameter models, so where either the dimension of the Kähler moduli space or the mirror complex structure moduli of the mirror space is 1. This is not really a strict restriction. So many of the statements I'm going to make straightforwardly but tediously generalized to higher parameter models. What I will exclude is truly non-geometric compactification where the dimension of the Kähler moduli space is 0. So WAFA recently has some interesting discussions on non-geometric backgrounds that will not be covered in this talk. In the context that I'm discussing, I will mostly be on the type 2a side. So I will focus on the Kähler moduli space, where the moduli are complexified volume parameters, and it makes sense to talk about large volume and small volume. And this is the language I'm going to use. And of course, thanks to mirror symmetry, there is a mirror statement, but this is not what I'm going to talk about. So it's all going to be the type 2a picture. And also, I want to re-emphasize that I'm only studying asymptotic regions of the moduli space, so where the moduli are large, might be negative, but large. And this excludes certain loci in the middle of the moduli space. And for instance, the techniques I'm using can say something about this, for instance, about these conifold points, but they're not as strong. And there are interesting loci in the moduli spaces, for instance, attractor points or so-called desert points that play a role in swamp line conjectures that I will not be able to address directly. So we're really sitting in the asymptotic regions. All right, and for the B branes, I will not touch A branes because I'm doing compact Calabi-Yaus and this is too difficult for me. It depends a little bit. So they are all in infinite distance limits, but it depends on which metric you're using. Yeah. Let me go a little bit more to the examples. It's a good question. So some of these limiting points will be at finite distance if you use the appropriate metric, like Landau-Ginzburg points. But in the parameter space I'm using, it would still be like at infinite values of those parameters. But if you use the correct true metric, some of these points, not all of them, will be at finite distance at the moduli space. Okay, please ask me again if it's not clear. Okay, so now let's be more concrete. How to address these questions. So one of the strongest tools, of course, that we can have is mirror symmetry in topological string theory. This is very well developed and also has the technology to study like these distance regions of the moduli space. And I want to highlight one paper that included Mingxing together with Albrecht Klemm and Quackenbush. And this is really a workhorse to do like explicit calculations. If we go to the distance regions in the moduli space, it's often more a question of interpretation of how to interpret the results we're computing. So even though we're using this all the time, I will not talk about this because I'm a GLSM person. So what I'm going to do is I'm going to discuss gauge linear sigma models. And so for those who don't know, a gauge linear sigma model is more or less a physics tool to probe the global structure of the Kähler moduli space in a Calabi-Yau context. You can also do non-Calabi-Yaus, but I'm focusing on the Calabi-Yau case, and Mauricio already gave a nice introduction this morning if you've been here. All right, so if the next slides are going to be a little bit technical, so if you don't care about the technical details, you can have a post-lunch nap right now, and I'll just give you the executive summary of the next 5 slides. Basically what the GLSM can do, it can probe the Kähler moduli space, the full stringy Kähler moduli space directly. And the reason how it can do this is that the GLSM as a supersymmetric gauge theory has Fi parameters and theta angles, and they can be identified with the complexified Kähler moduli. So the GLSM comes with a notion of phases that depending on where you are in the moduli space, you have different low energy effective theories and different vacua, and this puts you in different loci of the moduli space. So this is sort of the reason why GLSM is so useful. And another important thing that also Mauricio addressed in his talks is that via supersymmetric localizations, we can compute a lot of partition functions exactly, which also allows us to compute quantum corrections that are moduli dependent, Kähler moduli dependent, directly in the GLSM without using mirror symmetry. And this is going to be the rest of the talk. All right, so let's go into the details about GLSMs. So a GLSM is a 2D 2,2 supersymmetric gauge theory. It is neither topological nor conformal. So we have the standard 2,2 worldsheet supersymmetry and the associated U1R symmetries. And in addition, we also have a gauge symmetry with a gauge group G, which is not necessarily abelian, but when it's abelian, it's related to the toric geometry setting. The field content consists of chiral multiplets and vector multiplets. I only ever give the scalar components because I'm going to look at the vacuum structure of this theory, and this is determined by the scalar fields. So the matter sector contains these scalars that live in some complex vector space, and they transform in some matter representation of the gauge group, and the gauge charts is just the weights of this matter representation. And what makes a GLSM Calabi-Yau is actually an anomaly cancellation condition for the axial anomaly that gives a restriction on the weights on the allowed weights of the representation, and that makes a GLSM Calabi-Yau. If the charges sum up to 0, you have a Calabi-Yau GLSM. It's not geometric at all. And the vector multiplets are just Lie algebra valued fields, and just for the notation, you have to remember the phi's, they correspond to the matter sector, and the sigmas, they are the scalar components of the gauge sector. So as I already said, the GLSM also has coupling constants. There are the gauge couplings, I will suppress them, but they are there. And the parameters that we need to pay attention to is this Fi theta parameters, as many as the rank of the gauge group in principle, but we have to be careful with that. And these usually get renormalized, but not in the Calabi-Yau case, so they are true parameters. And it so happens, when you look at a full quantum GLSM, that they always come in a complex, they combine themselves into a complex number. And this combination I will call T, and this will be the coordinates on MK. So these are coordinates on the Kähler moduli space. And I will exclusively talk about compact Calabi-Yaus, and if you want to engineer a compact Calabi-Yau in a gauge linear sigma model, you have to turn on a superpotential. Okay, let's talk about the phases and the low energy configurations. So as I already said, phases of the GLSM are low energy effective theories depending on the values of the Fi parameters. I only write Fi parameters here because we first do a classical analysis and then we will see the quantum sector appearing. So when we talk about phases, we first have to talk about vacuum configurations of a GLSM. We have to find out what the vacua are, and then it'll sort of expand around this vacuum to see what our low energy effective theory is. So as we already heard in Antoine's talk, there are Coulomb branches and Higgs branches. So a general GLSM has a very complicated vacuum structure, but I will zoom in on those which are sort of the most important ones. One type of vacua are the Higgs vacua, where the gauge sector completely decouples. So basically the vacuum, the classical vacua of the GLSM are determined by the solutions to the D term and F term equations. So the mu here is a moment map equation. I'm not writing this out explicitly. If you have the data of the GLSM from the previous slide, you can just write down these equations and then you need to try to solve them. And what's important in here is that the Fi parameter enters. And the fact is now, especially when these parameters change the sign, the solutions to this equation can change. So what will happen is, at first, because we're looking at a vacuum, the gauge symmetry will be broken. So it can be broken completely. This is what would happen for like the well-studied Calabi-Yau cases. But it could also be broken just to a subgroup. And this may even be a continuous subgroup. And because of this Fi parameter dependence here, the parameter space will be divided into chambers where we have different solutions, and this would correspond to different Higgs branches. And for the toric geometry experts, these chambers correspond to the secondary fan associated with the toric variety. So that's why we can see the global stringy Kähler moduli space. And once we have the vacua, we can go on and think about what this low energy effective theory around near this vacuum is. And this is basically a GLSM analysis that you have to do. So this is just one type of solutions to the vacuum equation. So there's also a Coulomb branch. And in this context, the gauge sector will be sort of the dominant and light variable. So the matter will be massive, we can integrate it out, and the low energy effective theory is governed by the gauge symmetries. And this will actually tell us something about what's happening in the middle of the moduli space. So this will tell us something about the structure of the phase boundaries. In order to analyze the Coulomb branch, you have to go away from classical physics. Analyzing the classical vacua is not enough. But luckily, because this is supersymmetric, you only have to go to one loop. And you get an exact expression. So what happens basically is that the sigma fields, which are classically massless, get amassed by quantum corrections. And you can write down an effective superpotential, and then the Coulomb branch is located at the minimum or the critical set of the superpotential. And what's important in here is that the Fi theta parameter enters. And again, you can write this down explicitly if you have the GLSM data. And this will determine the singular loci, the mirrors of the conifold points, to say, in the moduli space. And that really depends on the fact that you have a complexified Kähler parameter and not just a real parameter as a GIT description would have. And so this sort of, the Higgs branch determines the phases, and the Coulomb branch determines the phase boundaries. Roughly speaking, if you work more generally for higher rank gauge groups, there can also be mixed Coulomb-Higgs branches, which is more complicated. And when you have non-abelian gauge symmetry, then also strong coupling phenomena can enter. Okay, so this already makes the GLSM quite useful. Another thing we can have in the GLSM is that we know very well, thanks to Herbst, Torrey, and Page, how to describe B-type D-branes in a GLSM. And so basically, as Mauricio already told us in the morning, B-type D-branes are G-invariant matrix factorizations of the GLSM superpotential with R charge 1. If you want to be a bit more technical, what you'll have to choose is a Chern pattern space, which is a set2 graded module where the boundary conditions basically can take values in. And a matrix factorization just means take a square matrix which has polynomial entries in these chiral matter fields such that it squares to the superpotential times the identity matrix. And any such matrix factorization will describe a B-brane up to some redundancies. I want to sweep under the rug. Mauricio will also scold me for not telling that there's also boundary conditions on the sigma fields, but please forgive me. Gauge and R symmetry can also be very much explicit and descends from the gauge and R symmetry that we have in the bulk fields. So this is a very, very non-geometric description of a B-type D-brane. It doesn't rely, there's no cycles and vector bundles everywhere. So and this is also maybe one first hint on the universal structure that we see in the description of certain objects. So if we, no matter how we describe the phase, the IR description, the UV description of a B-brane will always be this matrix factorization. And then when we go to a phase that should be a geometric phase, then this will reduce to objects in the derived category of coherent sheaves associated to the phase. So this is one notion of this universal structure, and that matrix factorization is sort of the right thing to do globally on the moduli space. Okay, so I think this already was very well established in the 90s and 2000s. So what made the GLSM much better than it used to be was the realization that you can apply supersymmetric localization onto GLSM. It's a nice SUSY gauge theory. We can do this. And for certain curved backgrounds, the path integral can be solved exactly. And it turned out, if you apply this to Calabi-Yau GLSMs, these SUSY partition functions compute fully quantum-corrected objects that are of interest in string compactifications, compute quantum corrections, and also in various phenomenological applications. So here's a bit of a phone book of the things that can be computed. It's incomplete, but the sphere partition function, for instance, turns out to compute the exact Kähler potential on the Kähler moduli space, which then gives the metric on the moduli space, the true metric on the moduli space, which lets you decide whether a point is at a finite distance or not. The torus partition function computes the elliptic genus. The hemisphere partition function computes, as Mauricio told us in the morning, the central charge of a B-type D-brane, including quantum corrections. And the annulus partition function computes the open Witten index. And all these partition functions are contour integrals, and especially those I'm going to discuss depend on these Kähler parameters, on the Fi theta parameters. So basically, you can evaluate these partition functions in a phase by closing the contour in such a way that you get a convergent result. And that sort of accesses different regions in the moduli space by basically choosing which poles contribute to these complex integrals. And so these objects, in principle, can be evaluated in any phase of the GLSM, irrespective of whether we really know what the right low-energy effective description is. And that can be very useful, and that's another notion of the universal structure. So the claim first started in Landry-Ginzburg models, but probably we believe it's true much more generally, is that the partition functions evaluated in the phases should have some sort of a universal structure. So that was in a paper with Mauricio and Emmanuel, and then in some follow-up papers with my students. So for instance, if we take the hemisphere partition function, which depends on the B-brane in the GLSM, and we evaluate it in any phase, our claim is that we can write it in terms of objects that we should in principle be able to define in any of the phases. So what we see here, our claim in this paper is that you can be, the result after you evaluate in the phase can be written in terms of a pairing on the state space of the IR CFT, the topological pairing, and then there is a gamma class that appears, there is an I function or J function that appears in the sense of Giventhal, and there is something that we should identify with the Chern character of a brane. And we tested this in geometric phases and Landry-Ginzburg phases and also other examples that I'm going to give you. And all of these objects can actually be defined or should be definable without reference to any geometry. And that makes this universal. We can also turn this around. So this is a conjecture, and in some sense it has been proven, but you can also assume that a conjecture is true and apply this to a phase that you don't know, and then get conjectures of what the I function or the Chern character or the gamma class should be. And this actually, you can, for instance, apply to compute this genus zero invariance, so the generalization of this, of the genus zero conflict invariance, D-brane charges, basis of periods of the mirror, all that kind of things, or swampland distance conjectures if you're a phenomenologist. All right, so this is sort of the tool set that I'm going to use for the GLSM, and in my last 25 minutes, I'm going to do a lot of examples of what can happen at the other end of the moduli space, and what the status is, and how much we can compute and how much we understand. Yeah. Yeah.
There are some conditions like this.
Yes.
This object
Yeah, I can calculate this even in region of the moduli space where I don't have a smooth compact Calabi-Yau geometry. And I can, in some cases that are where I understand what's in the limiting region of the moduli space, I can then sort of define this object intrinsically in the low energy theory as well. And for instance, in the paper with Maurice and Emmanuel, we did this for a large class of Landau-Ginzburg models, pretty much all of them actually. Okay, since I talk about Landau-Ginzburg all the time, let's do the quintic. So I'm not claiming any originality here, so the quintic has been very well understood, but it's what we have to do, right? If you want to realize the quintic as a phase of a GLSM, you get away with a U1 abelian gauge group. You choose 6 fields. One of them has charge -5, and 5 of them have charge 1 under this gauge symmetry. It's a rank 1 gauge group, so you only have 1 sigma field and 1 Fi theta parameter. And the superpotential that's gauge invariant is linear in P and already suggestively degree 5 in the axis. And the translation really is that the chiral scalars will be the coordinates on the Calabi-Yau. So then with this data, you can write down explicitly the D-term and F-term equations, which I will not do, and you can analyze the vacuum of the theory. And that will be sensitive to the sign of the Fi parameter. So when the Fi parameter is positive, the solutions to the D-term and F-term equations on the Higgs branch will tell you that the P field is set to 0, and the x's get constrained to live on a P4, and actually on a quintic hypersurface in P4. So the vacuum manifold of this GLSM is the quintic itself. And then the associated low energy effective theory would be a nonlinear sigma model, 2,2, with Calabi-Yau target. So the gauge sector is gone, and we're left with a nonlinear sigma model on this Calabi-Yau. If you go to negative Fi parameters, so the Fi parameter in the geometric region would be just like the volume parameter, right? But that doesn't make sense if we put that to negative values. So something else happens. So what you will see if you just do the vacuum, you actually find that the vacuum is a single point. Which means all the x's are 0 and P gets a vacuum expectation value. And the point is not a Calabi-Yau threefold, obviously, so we have to work a little bit harder to see the full structure. So we see that the gauge symmetry, because this P field has charge -5, is actually not completely broken, but only broken to a set 5, so we'll get some sort of an orbifold. And if we then turn on classical fluctuations of the x fields, this quintic potential is generated. So the low energy effective theory will be set 5 Landau-Ginzburg orbifold, which is not a geometry in a traditional sense. It's not a smooth Calabi-Yau manifold. So you have a singular space plus a potential. And if you then go on and insert all these charges into this formula with the Coulomb branch potential, you actually find that there's a Coulomb branch right in the middle of the modular space. It's a singular point. So if you remember from 30 minutes ago, my cartoon of the one-dimensional moduli space, stringy Kähler moduli space, this is what it looks like for the quintic. So we have a large volume region where we have the smooth Calabi-Yau. We have some singularity, mirror conifold point in the middle, and then we have a non-geometric phase, which is a Landau-Ginzburg orbifold theory. So this is the first example of a something else. And what I also want to emphasize is that there is like a path through it. You can avoid the singularity, so you can smoothly interpolate in principle between Landau-Ginzburg and Calabi-Yau. And this is where all the equivalences come from. So let's go through a list of things that I listed in the general section of this talk, of the questions that I would like to answer. And pretty much for these Landau-Ginzburg orbifolds, all the questions can be answered. So one important thing for Landau-Ginzburg is that this is a theory with an action. It's a 2,2 Landau-Ginzburg orbifold. You can write down a Lagrangian, and Waffer and Intrigligator Waffer already at the end of the 80s told us what the quantum state spaces are. They are called twisted sectors. They have nothing to do with cohomologies of a Calabi-Yau threefold, but they encode the same information. You can then take the AC chiral ring elements associated with twisted sectors and insert that into genus zero correlation functions and define the Landau-Ginzburg version of a Gromov-Witten invariant. So from a physics perspective, this is just a correlation function at 2,2 CFT, so it doesn't really matter if there is a Calabi-Yau anywhere. And it's actually the mathematicians who've done a lot of work for us defining this Gromov-Witten analog, which is called FGRW theory for Fan, Chavez, Ruan, and Witten. And what we've shown in this paper from 2020 is also that these FGRW invariants, these Gromov-Witten analogs, can be computed explicitly by exploiting these universal structures of these stringy partition functions. So this is a strong computational tool that applies not only to geometry. And B-branes are in a very good state. So in the early 2000s, based on an idea by Kontsevich, Kapustin, and Lee, showed that B-branes in Landau-Ginzburg models are also matrix factorization. So the connection to the GLSM is actually very straightforward. And there is a lot of work since then. Also, the connection to CFT is well understood. So Matthias has contributed a lot to this. And what you can also do explicitly, thanks to this paper by Herbstor and Page, is you can actually, let me go back, use this, like, the fact that you have paths in the moduli space to analytically continue B-branes from Calabi-Yau to Landau-Ginzburg. So you can really transport them on a given path. And this has been, if you want to read wonderful 265 pages of a paper, this is where you get explained everything. It's also really practical when you combine this with the partition functions, because, for instance, you can, if you're transporting D-branes around singularities, you can, this is a way to compute monodromies, like say conifold monodromies, analytically, algebraically, without using any numerics. So using B-branes actually does a lot of good things that are maybe a little bit harder using mirror symmetry. Yeah, and also before Kreutzer and Skarke classified polytopes, they classified polynomials. So the Landau-Ginzburg orbifold models are actually also fully classified. So this is the best we can have. So let's go to something which is not as good, please. Yeah. You don't really need both. You can use, sorry, it means you can use either. So if you're computing like true closed string information, like if you just want the I function or the periods, or you can do either this or that. So for the genus zero invariance, you can extract this both from the S2 or the D2. So you need the state space and you need the I function basically, and the state space determines the mirror map. That gives you the right coordinates for the expansion in terms of these correlators, and then you're fine. All right, good. So let's move on to something which is slightly more exotic, but still very well under control, and this is what I've spent my days with in the past few years. This is what's called good hybrid models. So I'm not going to give a definition of a hybrid model because it's too technical for the style of talk I'm giving today. Morally speaking, a hybrid model is a hybrid between a Landau-Ginzburg model and a nonlinear sigma model. So you can view this as Landau-Ginzburg orbifolds, as we just had, fibered over some geometry, as we just had, like a P1. And that's already in Witten's paper, and also Bertolini, Melnikov, and Plesser in 2013 and onwards studied these hybrid models. The question is whether this, yeah, Landau-Ginzburg model is a special case of a hybrid in the sense that it's a Landau-Ginzburg orbifold fibered over a point. And the nonlinear sigma model with Calabi-Yau is a special case in the sense that the base itself is the Calabi-Yau and the vibration is trivial. So this generalizes Landau-Ginzburg and nonlinear sigma models. So the question is, where do they appear? And they appear actually quite frequently. And since I'm mostly talking about one-parameter models, you may or may not know that Mauricio had already told us that Calabi-Yaus have associated Picard-Fuchs equations and period integrals. And if you look in the one-parameter case, 14 of these Picard-Fuchs operators are actually hypergeometric operators. And the associated Calabi-Yaus are all some complete intersection in toric spaces. So it's very easy to write down the GLSM and look at what the other phase is. And 3 out of these 14 hypergeometric Calabi-Yaus have one of these good hybrid models as the other phase. So for instance, if you take the 3 cubics in P5, the phase at the other end of the moduli space will be a Z3 Landau-Ginzburg orbifold fibered over P1. And also if you look at other like multi-parameter Calabi-Yaus that have been very well studied in mirror symmetry, the associated GLSMs will also have these good hybrid phases. So they are fairly common, and also when you look at them in non-abelian GLSMs, you'll find them. Good, so how much can we do with hybrids, with these good hybrids? So actually quite a lot, and again, the good advantage is that we have a theory with an action. This is what was worked out by Bertolini, Melnikov, Plesser. So basically it's a nonlinear sigma model with a potential. The nonlinear sigma model is, of course, on a non-compact auxiliary geometry. And then some extra conditions that makes this vibration well-defined. So again, you have a nice 2,2 theory, and you can actually construct also the state spaces explicitly, and it will match Hodge numbers in the geometric phases and so on. And because you have so much control about the state spaces, you can actually also compute these analogs of chromophytin invariance again. Emily Clader and then also other authors define this in the mathematics literature. And again, we can use, and this is the work of myself with my PhD student David Erkinger, you can use the sphere partition function or the hemisphere partition function, whatever you prefer, to explicitly compute these analogs of chromophytin invariance in these hybrid phases using the GLSM. And yes? Yes. So the GLSM potential, for instance, yes. So if you start off with the GLSM and the potential, you will see that the vacuum manifold is sort of, let me go back here. The vacuum manifold is a geometric base. So for instance, the vacuum manifold is a P1. And the GLSM potential will depend on all the coordinates. And basically, the P fields get a VEV, and the other fields that are 0 in the vacuum that you turn on as classical fluctuations then generate this potential. So it looks like a Landau-Ginzburg model, except that sort of the base of the Landau-Ginzburg model is not a point, but a geometry, defined by the non-Calabi-Yau vacuum manifold. Yes, it's a holomorphic function. It's complex. This here, so this one has a P1 base spanned by the coordinates that have weights 1, 1, and it's a K3 vibration. And so basically, so this model is a K3 vibration. It's a K3 over P1. And you can picture the hybrid phase as the P1 staying what it was and the K3 undergoing a Landau-Ginzburg transition. And the second example is an elliptic vibration. So the base is a P2 spanned by the coordinates that have weights 1, 1, 1 here. And you have the standard elliptic fiber. And the elliptic fiber undergoes a Landau-Ginzburg transition. Please. Okay. Yes. No, you don't really shrink. So you shrink it and then blow it up again, but in a geometric region. Yes. So in this, the last two have 2 parameters. So one is the volume of the base that stays large volume, and the fiber coordinate sort of goes to Landau-Ginzburg region of the modular space. So you shrink it. Yes. Okay. Good. Let's move on. I have like 10-ish minutes left, so I should speed up a little. So we've already done that. So I think thanks to my PhD student, Robert Pryor, who just graduated and will move to China very soon. We also know hybrid B-branes very well. He derived this basically from the boundary action of this 2,2 NLSM and found results consistent with earlier works in mathematics and physics. And also this whole story about D-brane transport monotomies works very well. What's not known is a classification of this good hybrid model. So we don't know how many good hybrid phases there are, in contrast to what we know about Landau-Ginzburg theories. So I keep talking about good hybrids, and that should already suggest to you that there are hybrids that are not good. So this is so the good news ends here. So let's come to the bad news. There's also something called bad hybrids and pseudo-hybrids. And I don't know. I don't know that. Sorry, I'm not familiar with this. We can discuss later. Yeah, I don't. Probably yes, but I don't know. All right. So I don't think there is. I think there should be a finer classification of what not good hybrid models are. But for the sake of this talk, is everything that's not good in the context of the previous examples. So I'm just giving a few examples of what can go wrong in these descriptions. So I think that the most striking thing is that when we have the F-term equations and we try to solve them, it can happen that they don't have a unique solution. So it could be that there are several branches that emit different symmetry breaking patterns, and that already means that the R charge of the CFT will not be uniquely defined. So we can have different branches of solutions to the D-term and F-term equation in the same phase. It can happen when that the CFTs that are in these regions are singular in the sense that they behave like a conifold point. So we have extra massless fields. In non-abelian GLSM, something even worse can happen. Horry and Tong call this non-regular, that the gauge sect of the GLSM doesn't fully decouple, and so you don't really have a proper Higgs branch anymore. So I think what all of these bad phases have in common is that there is no known formulation of a low energy effective theory in terms of an action. So I know to some people in the audience, having a theory without an action is not a bad thing, as we heard in the previous talk. But for me, this is still somewhat scary. But I think we'll also have to deal with this also in the Calabi-Yau moduli spaces, because I actually believe that this is a generic phase of a GLSM. The examples I gave you before are probably non-generic at all, and we'll have to deal with sort of phases of GLSMs where we don't have a nice description, low energy description in terms of an action. And they are ubiquitous. So going back to the 14 hypergeometric examples, 6 out of those have a bad hybrid phase. The good news is that the GLSM partition function and mirror symmetry often give sensible results. So they give a window into these phases we don't have a description that is as good. Okay, so I'm going to stop with the bad news and the non-geometric things. Yeah. No. Horry, who used these words, I don't think he knows about non-regulatory English. This is recorded. All right. Sorry. Not necessarily. So these singular ones are often, but we also have these non-regular things, and they can be at infinite distance. And I might make it to an example. No, I don't think they do. So the reason is that they come in projective spaces, and you can. So this is one example of a modular space where it can happen, and basically you don't have a nice vibration structure there. Or you only have it like locally for different solutions of these vacuum equations. Okay, so let me come back to geometry, because so this is as non-geometric as it gets. So let me come back to another class of examples that can happen. So what I'm just going to discuss in my remaining 7-ish minutes is to talk about what happens when there are other geometries at the other end of the moduli space. So, and for the sake of this talk, I will suspect that there is a geometry if we have another point of maximally unipotent monodromy at the other end of the moduli space. But that's only a working hypothesis. And this is something that happens very frequently, for instance, in toric GLSM. So you find another smooth Calabi-Yau geometry. The Calabi-Yau is topologically distinct but birational. related by a flop transition, and in toric setting, this corresponds to having different maximal star triangulations. So this is very, very general, and these are not the examples I want to talk about. So what I want to talk about is Calabi-Yau moduli spaces that have 2 points of maximally unipotent monodromy, where the corresponding Calabi-Yaus are not birational. Sometimes they are non-commutative resolutions of some singular spaces, as Mauricio already mentioned in the morning. And the geometry itself doesn't appears through non-perturbative effects and not just like a solution to the vacuum equations. And also these non-regular models, which are totally off, they can have, this year we found an example which has a point of maximally unipotent monodromy, which really baffled us. And maybe I'll come to that. And that would be an infinite distance point. Okay, so to give the standard example, so this is like the cousin of the quintic. So if you want to understand non-abelian GLSM, you should study this model. This is the Rutland model, after mathematician Rutland, who first realized that there are two non-birational Calabi-Yaus inside the same moduli space. Horry and Tong in 2006 realized this in terms of a GLSM. It's a U2 GLSM, so we're leaving the toric regime. We have 7 P fields like we had for the quintic. They are singlets, they transform in the determinantal representation, and 7 fundamental fields. We only have 1 Fi parameter because the rank 2, but only 1 Fi parameter because of the Weil symmetry of U2. The superpotential is something that already Mauricio has written down in a similar setting. So it's an antisymmetric bilinear in the fundamental fields and linear in the singlet fields. And you already can see that this antisymmetric linear 7x7 matrix in terms of the P field can be understood as a mass matrix for this quadratic term. So you can write down the vacuum equation, doesn't matter what they look like, and you can study the phases as you can in the other examples. So the large volume phase is very, very simple. So it's like the quintic. So the P fields get to 0, and the Calabi-Yau is the vacuum manifold itself. The gauge symmetry is completely broken. These antisymmetric bilinears become Plücker coordinates on a Grassmannian G27, and we have put in a complete intersection of codimension 7. And that's a Calabi-Yau threefold. Non-toric, but fine. What's more interesting is this small volume phase, and this is where this non-perturbative geometry comes in. So the vacuum itself is not Calabi-Yau, it's a P6 with the P fields, and the x's are 0. And that shows that the gauge symmetry is actually broken to SU2. So the low energy effective theory will still be a strongly coupled theory. It will be a gauge theory. And then Horry and Tong had to work very hard and use Born-Oppenheimer approximations to show that at very low energies, the gauge sector eventually decouples. And we have something like a hybrid model at intermediate energies, which is where you really have the x degrees of freedom and the mass matrix given by the VEFs of the P field. And this theory is trivial for general loci in these mass parameters, but there is non-trivial because this is a massive theory, so you would expect the CFT to be trivial. But because this is a mass matrix, there is non-trivial physics where the rank of the mass matrix drops. And this gives the geometry in the IR, the second geometry. So the geometry is a determinantal variety that's determined by the condition that the rank of the mass matrix drops. You also have a Coulomb branch, and I see I have to speed up a little. So to summarize the Rutland model, x and y turn out to be non-birational. You have 2 geometries. X is a complete intersection in non-toric variety, y is a non-complete intersection. Y is a strongly coupled phase, and the geometry is realized non-perturbatively. And D-brane transport is interesting. We're in year 11 of a paper with Mauricio and Richard Eger and Kentaro Horry. I don't know when it will come out. I don't want to talk about it. So let's move to my very final example. So I had another example, but thanks to Mauricio, I don't need to talk about this. The last thing I want to discuss is non-commutative resolutions. So another source of points of maximally unipotent monodromy is that you look at Calabi-Yaus that have nodal singularities. And instead of blowing up the singularity, which would add a killer parameter, if you have torsion in your homology, you can turn on a discrete B field. And this discrete B field stabilizes and non-commutatively resolves the singularity. And it was recently found by Thorsten Schimanek and Katzklem Schimanek-Sharp that this also modifies the topological string partition function, and you can actually define a torsion refinement of the Gopa-Kummer-Waffer invariant. So topological string theory works also on these non-commutative resolutions, and that led also to a lot of new examples of Calabi-Yaus, and also potentially interesting properties of the associated D-brane categories. So the simplest example is a toric example, which Mauricio implicitly had in his talk, so I'm going to skip it, and move in my last minute to my most recent paper with Joseph McGovern. So basically, we found this model by looking at a Calabi-Yau equations database for examples which have 2 points of maximum unipotent monodromy. And we came up with this, and it really shocked us. So it's an almost toric model in the sense that you have 3 U1s and this field content, but you have a symmetric product with a set 3 which cyclically permutes these the 3 fields. We have a cubic superpotential or a trilinear superpotential, and so the interpretation as a mass matrix is out of the window. So this whole story with that I explained with the Rutland model didn't work. Let me just briefly say what we found. The large volume phase is nice again. It's like one of these very well studied free quotients, complete intersections in free quotients of a toric variety, a product of toric spaces. But the small volume phase is non-regular. So the GLSM completely breaks down. The gauge sector doesn't decouple. We don't know how to deal with it. So the low energy effective description is totally unclear. And it's strange that this point is still at infinite distance and still presents as a mum point. What still works is mirror symmetry. And when we assume that we have this structure of this non-commutative resolution, we can come to a crazy conjecture that even though we don't know what the geometry is, you should take this Calabi-Yau complete intersection, degenerate it to have 63 nodes, which we don't know how to do explicitly, and turn on a set 3-valued B field. And our conjecture is that this is sort of the dual geometry, even though the GLSM can tell us absolutely nothing about this, and this really comes from the coffee grounds that the higher genus invariants give us. All right, my time is over, so let me briefly conclude. I hope I convinced you that exotic regions in the modular space are ubiquitous. Some of them are well understood because they have actions, many cannot, but GLSM partition functions still work. Mum points don't necessarily lead to smooth geometries. Pays off to consider Calabi-Yaus in non-toric spaces. And there is some sort of a universal structure given by the CFT and the GLSM. So there are a lot of open questions. I think the main question is what is a good description of a generic limiting region in the Calabi-Yau moduli space when everything breaks down? And I haven't mentioned some interesting connections to mathematics because I wanted to give a physics talk, but I just leave them out of here. And I know you're getting nervous, so I'm stopping now. So thank you for your attention.
Do we have questions?
Question. How do you characterize this bad hybrid and good hybrid in this hypergeometric case?
So the good hybrid are just what I said. You have a Landry-Ginsburg-Orbifold fiber or a base.
I just read from geometry directly.
You can read this from the geometry directly. For the bad hybrids, you in principle can also read it for the geometry. So you need to look at the vacuum equations and appreciate that they have 2 solutions, like in the small volume phase, like a point plus a line or something like this. And the symmetry breaking pattern are different. But there is no systematic, so you have to analyze it case by case.
Can you distinguish this from the monodromy of the negative point?
That's what we thought. So usually the monodromy, so there are not really, because for instance, this hypergeometric, the bad hybrids are both F-type and C-type. Yes. But we have a bad hybrid which has maximally unipotent monodromy. So
like the double of it.
Yeah.
I mean, then in principle, we just need to look at this AKSZ table and we classify all the 1 parameter cases.
Yeah, but that doesn't work because you can even have a mum point in the bad hybrid.
Oh, I mean, even in these bad hybrid cases?
Yeah, so that's the last example. It's a mum point, but it's a bad hybrid.
But is this extra index of the mum point like matter somehow?
We haven't checked this. I need to. Yeah, we have it in our paper, but yeah. Yeah, and that's infinite distance because it's a mum point.
Okay.
It's a puzzle.
Thank you.
When you pass between these different phases from the target space perspective, what shrinks? Is it 2 cycles in 2 cycles, 4 cycles, or even the entire Calabi-Yau volume?
It's 3 shrinks because it's like a conical transition.
Say again.
In a mirror, and it's 3 shrinks, and in the like type 2A picture, it's the structure sheaf itself, the OX that shrinks, which is like Strominger's black hole. Sorry.
When you talk about this non-commutative resolution, somehow you have this portion of this Kubku alpha inference. Yeah, it's a torsion refined. So this should be resolved by this turn on this discrete B field.
Yes.
But I thought when you talking about Wafa, you go to MC.
So this is a paper by Wafa and Witten where they studied this in the local case.
Yep, my pattern is that in M0 you don't have a B field, but it seems that this B field is kind of crucial.
Yeah, so in this case, they talk about the B field and resolving the singularity looking at the B field. More than one paper, maybe.
Last question? So let's thanks again. So